Hello and welcome to another installment in the series The Ray Tracer Challenge, where I'm usually implementing a ray tracer based on the book The Ray Tracer Challenge by James Buck in Rust, and then compiling it to all sorts of different targets, like for example WebAssembly to run it in the browser and stuff. This session today will be a little bit different because I have gotten over the time a lot of different questions regarding why we are actually using 4x4 matrices in our ray tracer and why are we using four-dimensional vectors in the three-dimensional world. So I've already my iPad here prepared to do a session with you on why and how this actually is done and why we are using 4x4 matrices and four-dimensional vectors and what all of those components mean. So I would like to go ahead and explain this to you because, as I've said, it was asked a lot of times, and it will hopefully clear up why in 3D rendering in general 4x4 matrices are used, even though we are in a three-dimensional realm and a three-dimensional system where we want to describe movements and rotations and translations and stuff like this. So yeah, let's start, I guess. We are in the three-dimensional space. Therefore, we would assume that if we have some sort of point, it would be fully sufficient to have it defined with three coordinates, an x, a y, and a z, to represent its position inside a three-dimensional space somewhere. And actually, if we assume that, we are correct. This is enough to represent a point specifically in a 3D space. So why are we actually using four-dimensional points? The answer is quite simple. It makes things a lot easier for us during calculations and during processing of those information and points. But why is a little bit more involved to explain. What we are doing a lot within our calculations is we are using matrices. So we are multiplying our points, our vectors, and all that information with matrices quite a lot, and we are multiplying matrices with matrices and so on. So let's take a look at all of those different operations, or at least at some of them, to get a feeling for why we might need a fourth dimension for our points or our vectors, and what that actually means. So for example, let's see if we would like to scale this point with a scale matrix, and let's assume it's a 3x3 matrix for now. Let's define that. Let's call it MS, and it would be something like, for example, a matrix that scales by 2 would be 2, 0, 0, 0, 2, 0, 0, 0, 2. So now we have our matrix, which if multiplied with this point, would scale it. So in order to get a feeling for how all of this works out in the end, we need to calculate this multiplication of the matrix with the point. And in order to do that, let's just quickly write this out in a way that we can take a structured look at. So our new point would be actually then the matrix first. So 2, 0, 0, 0, 2, 0, 0, 0, 2, multiplied with our point 1, 2, 3. And now, how does matrix multiplication actually work? It's quite easy. This actually equals a new vector, which always consists of the products of the matrix row we are in with the column of the vector. So what does that mean? Actually, it means that we are multiplying this value here with this value here first. So 2 times 1 is 2, plus this value here, plus this value here. So 0 times 2 would then be 0, plus this value here times this value here. So 0 times 3 is 0. The next row would then be this value here times this value here. I think you get the gist of it. So we actually have 0 times 1, which is 0, plus 2 times 2, which is 4, plus 0 times 3, which is 0. And the last row would then be 0 times 1, which is 0, plus 0 times 2, which is 0, plus 2 times 3, which is 6. And if we now get rid of all the zeros because they don't need to be there, we have the vector 2, 4, 6, which essentially is the vector 1, 2, 3 scaled up by 2. So our scale matrix did its job quite good. So yeah, why do we need something more than a 3 by 3 matrix? It seems to work out quite fine. We can actually express something else with this. I could now show you how to calculate it out, like for example a rotation matrix and stuff like this, which works quite fine. We can actually create 3 by 3 rotation matrices and they work like they should and rotate our points in 3-dimensional space. So this works out quite fine. The real question here now is, what happens if we start to introduce translation, so movement of points in space? Because then we have a problem. We cannot express those within a 3 by 3 matrix. It's simply not possible to have a simple movement just along specific axes within a 3 by 3 matrix in the 3-dimensional realm. You cannot create any sort of matrix that, if calculated according to the rules of matrix multiplication, or a vector matrix multiplication in this case, will result in a specific translation on each of the defined axes. It simply does not work out. So how would we express a translation then? What we could of course do is we could go ahead and add this translation information in another way. We could, for example, do something like we want to have this scaling and we multiply it with the point and then we add another point. For example, the movement of 2, 3, 4. And this, of course, would work out. We would have been able to do this. And then we would have something like 2, 4, 6, which is our scaled vector, plus 2, 3, 4 here. And it would be 4, 7, 10. And yeah, of course, this would work. But the problem there is that we always would need to have this translation as a separate operation, and we could not combine those matrices, for example. And this is not what we want. But now, if we take a look and assume we can simply add to our matrices maybe another column, then this might work out actually. So let's take a look at this. Let's have something called the MT, our translation matrix. Our translation matrix now would be something like an identity matrix, which could be 1, 0, 0. And we have 0, 1, 0. And we have 0, 0, 1, which is an identity matrix which simply does nothing if multiplied with a point or a vector of 3 dimensions. And we now add another column, which we have here, which now has our translation which we wanted, which was 2, 3, 4 in the last column. But now, as our matrices need to be square, we of course need to add another row as well, and we choose to make the rest of the matrix the identity matrix. So we have a 1 in the bottom right corner. And now we have a 4 by 4 matrix. And for now, just bear with me what happens if we use this in calculation. Let's assume we now have our point here, our point P, which is now or has now a 4th component as well. And we are assuming this component is 1 for now. I will explain in a second why. So if we now have this component here, this 1, and we are now multiplying our MT matrix, so our 1, 0, 0, 2, 0, 1, 0, 3, 0, 0, 1, 4, 0, 0, 0, 1 matrix with our point 1, 2, 3, 1, then what would be the result? The result would be, let's see, 1 times 1. So we would have 1 plus 0 times 2. So 0. I will not write that out. Then we have 0 times 3. So 0 again. And then we have 2 times 1. And this one will, of course, then be a 2, because 2 times 1 is 2. So what are we going to have in the next row? In the next row, we actually have 0 times 1. We wouldn't want to write that out, but it is 0. Then we have 1 times 2. So we have a 2 there. Plus 0 times 3 is 0, and 3 times 1. So we have a 3 here. The next row would be then 0 times 1, so 0. 0 times 2, so 0 again. 1 times 3, so 3. Plus 4 times 1, though there will be 4. The last row will then be 0 times 1, which is 0, 0 times 2, which is 0, 0 times 3, which is 0, and 1 times 1, which is actually 1. And now, if you take a look at this vector, you will see that this one actually is our initial vector plus the translation that we wanted, so the movement. So we have actually achieved to create a matrix which, when multiplied with our vector, results in our moved vector. And this is exactly what we wanted. We wanted to be able to encode our translation within the matrix, because now we could combine this matrix with a scaling matrix or a rotation matrix or anything like that, and have everything in one matrix multiplication operation in the end. Now, of course, the question arises, why do we have this 1 here in our vector there? And what is it going to do to the vectors, and why is it there? And why are we, for example, using a 1 for points, and for vectors we are using a 0? That is essentially because a point in space can be moved. It is a specific point within our space, and we can of course move it. We can shift it along any axis, and we can therefore move it to another position. A vector, however, is something that only points into a specific direction. So if we have a coordinate system, for example, this one here, let's for now assume this is 2D because it is actually the same thing. And we have a vector in this coordinate system, like for example this one. It only is a direction. It doesn't really care where it starts. It is only relevant in combination with some sort of starting point, because it could be here, it could be here, it could be here, or it could be here, and it wouldn't make any difference. The vector would always be the same, because it is simply encoding a direction for us, at least in the way that we are using those constructs in our system. We are using a vector with a 0 fourth element as a direction. And only in combination with a point like this one here, or this one here, or this one here, or this one here, and therefore the specific vector that points to this point, and this is how we actually encode points in our system, is like we are always using a vector to that specific point from the origin of our three-dimensional space. Then we can do something with this direction. But this means that if we have a translation matrix like the one shown here, which moves everything by 2, 3, and 4, if it is applied on a vector which has then a 0 here in this place, if multiplied with this matrix, would mean that the translation would not affect this vector at all. It would simply stay the same. And now this is the reason here why we are using 4-dimensional vectors to represent points and directions in our space, and why we are using 4x4 matrices instead of 3x3 matrices, because we can encode translation within them. Why are we now especially defining this fourth part of this tuple we have there, a specific W component, and not a component which is either 0 or 1? Actually, this is the case because in certain 3D transformation operations, especially perspective transformation, this value might be something different than 0 and 1. And this value can be used for further operations to store some sort of information. Especially if we are doing perspective transformation, we can use the value to get back to our original value and our original point in 3-dimensional space, should we need it, if we encode this perspective transformation there. But we are not doing this in our ray tracer. Therefore, this is not that important for us here now. For us, it is important to understand why we are using 4-component matrices and 4-component vectors. Yeah, so I hope that this actually clears up things a bit, and that you now understand why we are using 4x4 matrices and 4x4 vectors in our ray tracer, and why those are used in the 3D world and 3D graphics world in general. Yeah, I hope you liked this video, even though it was quite a different sort of video where I tried to explain some 3D stuff to you. Please leave me a comment, leave me a like if you want to have more of those kind of videos, if you liked the way it was done, if you liked the question answered and the answer, of course, as well. And don't hesitate to ask me stuff like this. If you do not understand it, contact me via Twitter, via YouTube, or in any other mean that I'm reachable to you, so that I can actually know and answer those questions. I will do my best to give you feedback and to give you some more information to then think about this and make this clear for yourself. If you want to be informed about the next videos on my channel, please subscribe and hit the bell to get a notification there. And I hope to see you for the next video in the Ray Tracer Challenge, which will then most likely be coding again. So have a nice day and bye!